Okay, so when I look at the graphs given here, I should be able to tell just by the picture of the graph what the degree is. Okay, so when I'm looking at degree, I'm looking at what the ends are doing. So in the first graph here, I see that the ends are going in opposite direction, starting at the bottom in quadrant 3 and ending at the top in quadrant 1. So what does that tell me about the type of function? Well, that tells me it has an odd degree because the ends are going in opposite direction. I'm just going to fix this screen. Okay, what else do I know about this graph? Well, I know it's going uphill, right? It's an increasing function. It's going from the bottom to the top, so I know that means that it has a positive leading coefficient. And I could describe the roots. We'll have one root here, this root here, and these roots. This root here is called a real root because it's on the x-axis. These roots that turn, right, the roots that turn but don't pass the x-axis are called non-real roots. So if you had a cubic function, you would have 3 factors. One factor would be a real root because it will cross the x-axis, and then 2 of the factors will be non-real roots because they won't cross the x-axis. Okay, so the question says, state the type of function. I'm going to say that this one is a cubic function because it's odd and it turns twice, right? When I see it, look at the graph, it's got 2 turns. So the minimum degree it could be is power 3. Describe the roots. We have 1 real, 2 non-real. And are there any double roots? No. So remember that double roots are where the graph touches the x-axis but does not turn or does not pass through it. So when I look at B, again, the ends are going in opposite direction. It starts in quadrant 2, ends in quadrant 4. So that tells me it's an odd degree. It also tells me it's a negative leading coefficient because it's going downhill. I'm going to say it's the roots. Well, this one's a non-real root because it turns but does not pass through. And then this one is a double root because it sits on the x-axis but does not pass through it. It turns on the x-axis, so that means it's a double root. So I'm going to say this one is also power 3 because it has 2 turns and it has 3 factors, right? A double one and a single one. So that would make it power 3. Okay, so those are the types of things you should be able to determine from a picture of a graph. This one, I see that the ends are going in the same direction, starting in quadrant 2, ending in quadrant 1. So I'm going to say this is an even degree. It opens up, so I'll determine that it's a positive leading coefficient. It has 1 real root, and it would also be a double root because it turns on the x-axis but does not pass through it. And I'm going to say this is power 2 because it has a double root, so that tells me it has 2 factors, and it also has 1 turn. Turns once, so it's probably power 2. This one here, D, the ends are going in the same direction, so I know it's an even degree. It's pointing down, so I know it's a negative leading coefficient. It has 1, 2, 3 non-real roots because this is where it turns but does not cross the x-axis. Okay, and then it has 2 roots there that are passing through, right? So it's got 2 real roots and 3 non-real roots. Does it have any double roots? Perhaps. I would say, let's see how many turns this has. It turns once, twice, 3 times. Ends are going in the same direction, probably power 4. Okay? So I know it's an even degree, so it has to be either power 2, power 4, power 6, or so on. Negative leading coefficient. Okay. Let's see if there's any questions. Okay. All right, you also should be able to determine, maybe you don't have the graph, maybe you just have the equation. From the equation, you should be able to determine the degree, the sign of the leading coefficient, and describe the end behavior. So remember that the degree is the highest power. So in A, the highest power is 3. The coefficient on the highest power is the leading coefficient. So it's a positive leading coefficient. And then I would want to describe the end behavior. So I should be able to have a little sketch of this graph. I know it's odd, so it's going to go in opposite direction, and it's going to go uphill because it has a positive leading coefficient. I'm not really concerned about the turns or the x-intercepts. All I want to know is the end behavior. If it's positive and odd, it would have to start in quadrant 3 and end in quadrant 1. Regardless of how many times it turns or where those roots are. Okay, we'd have to start at the bottom and end at the top. This one has a degree of 2 and a negative leading coefficient. So if I were sketching that, it's power 2 and opening down, negative leading coefficient. So it would have to start in quadrant 3 and end in quadrant 4. So just from the equation, you should be able to determine the end behavior without actually having a picture of the graph. You should be able to sketch the graph. This one is degree 4 with a negative leading coefficient. So if it's negative, the end should go in the same direction and it should point down. So it'll probably look something like this. So it should start in quadrant 3, end in quadrant 4. The same as degree 2 with a negative leading coefficient. If I skip over to E, E has degree 5, positive leading coefficient, and it's a power 5, so it's probably going to turn 4 times. It's going to go uphill, and the ends are going to go in opposite directions. So 1, 2, 3, 4. It's going to look something like that. It should start in quadrant 3, end in quadrant 1. Okay, so you should be able to determine end behavior just by the equation. Okay, so that's most of the graphing wrapped up. The next thing that's in the guide is function notation. And so function notation is another way to write y equals. So f is the name of the function. It doesn't always have to be an F. It could be a G, it could be an H, could be whatever letter you want to use. Sometimes we use the letter if it's a application. So maybe we're measuring height, right? So I might say h of t is function notation, and that might be representing height in relationship to time. So f of x, f is the name of the function, x is the input or the x value. And then the 2x tells us what the function does. So it's the rule, right? So f of x equals 2x is the same as writing y equals 2x. So it's saying what is the value of the function when x is this value and the pattern is 2 times x. So they'll always give you a function. So in this case, f of x is 2x plus 7. It says find f of 5. So that means wherever the value of x is, it's saying what would the equation be if x was 5. So we'll replace the x with 5, and then we will just determine that value, which would be 17. If I want to find f of negative 3, this time I'm going to replace the x with a negative 3 and then calculate that value. It doesn't have to be a number. It could be a letter or an expression. So it says, well, what if x was a? So I'm going to replace x with an a. And then the only thing I could do at that point is simplify if possible. That one there's nothing to do, so that's my answer to a plus 7. I might be able to expand brackets. I might be able to collect like terms, but it doesn't always have to be a number. It can be a letter as well. So let's say we had a different function, g of x. So g of x equals x squared minus 6. So we want to replace x with whatever's in the bracket. So if I'm doing g of negative 3, I want to replace x with a negative 3. Make sure when you are substituting in, you use brackets, because sometimes we have to square, and we want to remember that it's negative 3 times negative 3, and we're not just squaring the 3 and we forget about the sign, right? So negative 3 squared is positive 9, and then that has a value of 3. This time it wants me to find g of a plus 1. So my x is being replaced by a plus 1, and that is squared. Okay, so in g of negative 3, we replaced x with negative 3. G of a plus 1, we replace x with a plus 1, and now we want to expand and then collect like terms. Okay, so remember when you're expanding a binomial, you have it twice, so you might want to write it out. If you can remember to multiply all terms, that's fine, but sometimes it's a good idea to multiply it out so that you don't forget the middle. And then once you've expanded, you're just going to collect like terms. Okay, we're not solving because it's not equal to anything. It's just an expression that we're substituting in, and then we're just going to expand it and simplify it. Okay. And the other thing we want to look at is composition of functions. Just give me 1 minute. Okay. So the other thing is composition of functions. So most times they refer to composition as an input-output machine. So you will be given 2 functions. And generally composition is written like this, f of g of x. So this open circle means composition. Okay, so you don't want to confuse it with multiplication. A multiplication looks more like a dot. So composition is an open circle. I can also write that as f of g of x. So this is how we read it. F of g of x. That's how I read that. So what does that mean? Well, that means that the inside function always goes first. So that means this function we always apply first, and then the answer to the inside function becomes the input for the outside function. So for example, remember that we have 3 ways to represent functions. We can use ordered pairs, or a table of values. We can use a graph, or we can use an equation. So let's say I had a set of ordered pairs. So f of x is these ordered pairs, and then g of x is okay, so we'll call this example 1. Okay, so let's say I want to find g of f of x. So g of f of x says start with f of x. So we start with f of x. And we look at the first point. So the first point is -1, and I look at the result, which is 3. So this -1 would be the input, or the x value, and the 3 would be the output, or the y value. The y value, or the output, has to be matched up with the input in the outside function. So I look at g of x, and I want to find a point that starts with 3. So this is sort of like the link, and then the final result is -2. Okay, so what does that look like in terms of the solution? The first point started with -1. So we started with -1. The output was 3. The input then becomes 3, and the final output is -2. So when you write your point, you write the starting coordinate x. The 3 is like the link, so it's not part of the answer. It's the value that links them together, and then the final answer is -2. And then I go to the next point. The input is 2, the output is 7. I look at g of x and see if there's a 7. There is. And then final answer is 5. So starting with 2, output was 7, which becomes the input in the next point, and then the final answer is 5. And then I go to the next point. Input is 5, output is 11. I look for an 11, there is none. So I can't use that point, okay, because there's no matching input in the other set. So the 11 does not match up with an 11 in the other set, so we can't use that point. So g of f of x would just be -1, -2, and then 2, 5, and then that would be it. Okay? If I did it the other way, let's say I said, well, let's do g of f of x, or sorry, f of g of x. So this time, we're going to start with g of x. So we start with the first point. The first point is 3, the output is -2. I look for a -2 in f of x, and there are no points that start with -2, so I can't use that. So I go to the next point, 7, 5. So starting with 7, the output is 5, and that matches with a point there, so I can use that. Final answer is 11. And then I go to the next point, 9. Output is -1. I see a -1 over here, right? That one matches, so final output is 3. So I get a different answer going the other way because I have a different starting point, and then I link it up, and then I have a different ending point. Okay? If you have an equation, did I write that here? Okay, so here we have f of x equals 3x minus 1. I'm just going to do this on a new page. So let's say we had f of x is 3x minus 1, and then g of x is x squared plus 2. It wants us to find f of g of 3. Okay, so we always do the inside function first. So we're going to do g of 3 first. So this is our x value. We want to figure out the y value that goes with it. So it's kind of like the ordered pairs, right? in the ordered pairs, the x value and the y value are given. If you have an equation, you have to figure out the y value. So g of 3, I'm going to put 3 into g of x and get my result. So that gives me 11. So that output becomes the input for f, the outside function. And then I put in 11 into f of x is 32. So that's my final answer. So you see the linking point, starting with 3, ending with 11. The output becomes the input for f of x, and then final result is 32. So f of g of 3 equals 32. Final answer, starting with 3, ending in 32. What if we went the other way? What if we wanted to do g of f of 3? Okay, so instead of starting with g of x, we're starting with f of x. So we would do f of 3 first. So f is 3x minus 1. So 3x is 3 minus 1. So that gives me 8. And then I would do g of 8. Well, g of x was x squared plus 2. So I'm going to do 8 squared plus 2 is 66. So g of f of 3 equals 66. Okay? So the input produces an output, and then that becomes the input in the other function. Final answer is 66. You can also do it with an equation. So it doesn't have to be a number. It might ask you to find g of f of x, or f of g of x. So f of g of x means substitute g of x into f of x, right? So instead of a number, I'm substituting in an equation. So f of x is 3x minus 1, and it wants me to substitute the x with g of x. And g of x is x squared plus 2. So I've replaced x with x squared plus 2. And then all you have to do is simplify. So expand any brackets, and then collect like terms. Okay, you cannot solve it because it is not equal to anything. If I wanted to go the other way, g of f of x, now I want to take g of x. So g of x was x squared plus 2. And I want to replace x with the inside function f of x. So x is going to be replaced with 3x minus 1. And that's going to be squared. So here I've replaced x with f of x, and then I have to expand it. So we'll just expand brackets, collect like terms. Okay, so that is composition of functions. We will look at that in a bit more detail in the next lesson when we do finish things up and do the review, but you should definitely be able to understand your graphs and looking at end behavior and degree and turns and roots, and also function notation, just the regular function notation, so where you're just subbing in values. Then composition where you're substituting in one into the other. Okay, I'm just going to see if there's any questions. Okay, so the 4, 5, just let's look at my schedule here.